Section: Introduction. In this section, we discuss how we can improve reasoning abilities in language models using chain of thought, COT, prompting, which encourages models to think through problems step by step. We find that longer reasoning chains tend to yield more accurate answers, emphasizing the value of this approach. Additionally, we note that integrating tree search algorithms, like Monte Carlo Tree Search, MCTS, with language models during inference can enhance performance on reasoning tasks, although it requires more computational resources. While previous studies focus on improving reasoning during inference, we explore a different approach, training language models to develop reasoning skills. Some research has involved training models using their own generated responses, employing methods like supervised fine-tuning or reinforcement learning. We also recognize that generating questions can effectively create training data, often using various data augmentation techniques. Recent findings suggest that supervising the reasoning process is more beneficial than just focusing on the final outcome, which applies to both reward models and language models. We aim to train language models with process supervision without relying on reward models, thus simplifying the training process. Our proposed methods involve a dataset of reasoning problems and their answers, which we refer to as P. Our goal is to enhance the reasoning capabilities of our target language model using this dataset without needing human annotations. We assume we do not have access to more advanced language models, ensuring our methods can be applied to the strongest available models. We illustrate our approach through a self-training method, where we train the models on data they generate themselves. We utilize MCTS to explore and sample reasoning paths, collecting training data from the search tree we create. This process of generating and fine-tuning the model is repeated until we achieve satisfactory results. For data generation, we create a training dataset D, where each entry consists of a problem, its partial solutions, the next steps in those solutions, and scores for those steps. We treat each step in solving a problem as a node in a tree, separated by two new line characters. We apply MCTS at each step to find the best next steps. The process involves several key stages. 1. Selection. We start at the root node and choose the child node with the highest upper confidence bound, UCB, until we reach a fully expanded node or a final solution step. 2. Expansion. If the current node is not a final step and is not fully expanded, we generate the next step as a new child node using the language model. 3. Simulation. From the new node, we continue sampling until we reach a final answer. 4. Backpropagation. We compare the final answer to the correct one, updating the visited nodes in the tree with rewards to inform future searches. After repeating this process, we build a tree where the child nodes represent the next steps of the partial solution. We calculate scores for these nodes based on their cumulative rewards and visit counts. We then add relevant tuples to our training dataset and continue the process until we reach a final step or hit a maximum length limit for solutions. Section Summary. In this section, we discuss our approach to enhancing the reasoning ability of LLMs through self-training, utilizing Monte Carlo Tree Search, MCTS, to generate step-by-step reasoning paths from a dataset of reasoning problems without requiring human annotations. We iteratively refine the model by sampling and fine-tuning on the generated data, ultimately aiming to improve performance on reasoning tasks while avoiding the complexities of reinforcement learning. Section: Iterative Training. In this section, we iteratively train the large language model, LLM, after generating training data from the previous iteration, beginning with a pre-trained LLM in the first iteration. During each iteration, we sample a specific number of problems from a set for data generation. At the ith iteration, we train the LLM by minimizing a loss function, where the first part represents the weighted negative log likelihood. We also include a KL penalty in the second part to address distribution shifts, which is a common issue in offline reinforcement learning. Essentially, our training approach can be seen as a type of reinforcement learning. For our setup, we apply our methods to LLAMA 3.1 to 8b instruct and DeepSeek Math 7b instruct, evaluating their performance on two well-known math datasets, GSM-8K and Math. We compare our results against two baselines, zero-shot COT and rejective sampling fine-tuning, RFT, which generates training data by sampling correct solutions from the LLM itself. To show that our data generation method is better than simply selecting the best and worst steps to create preference pairs, we also train LLMs iteratively on preference data generated this way, using DPO for preference optimization, which we call step-level DPO. For efficient training, we utilize low-rank adaptation, LoRA. In our main results, we present experimental findings that show our methods consistently outperform the baselines by significant margins, with accuracies improving during iterative training. However, we notice that performance converges quickly and does not continue to improve over more iterations. Consequently, we only use about 2,000 problems from both Math and GSM-8K for training. We also observe that performance converges faster on GSM-8K than on Math, likely due to GSM-8K being less challenging, making it easier for the models to learn. Notably, step-level DPO shows only slight improvements on Math, highlighting the superiority of our data generation method. For transferability evaluation, we note that the Math dataset includes high school math competition problems, while GSM-8K consists of grade school math problems. If the ILM's mathematical reasoning has improved, they should perform better on both datasets. Therefore, we assess the model's transferability by training on Math, GSM-8K and testing on GSM-8K, Math to confirm any enhancements in their reasoning abilities. Our results indicate that our methods outperform zero-shot COT on unseen datasets, confirming that they indeed enhance mathematical reasoning. However, the improvements are not as significant as those seen in non-transfer experiments, as the problems in the two datasets require different mathematical skills and knowledge.